Hello, everyone. Hope you're having a great summer so far and good day. Uh, I know I've been busy with work and oh, too much. Nobody wants to work anymore. But anyways, today I want to talk to you a little bit about my sorting and searching analysis, looking at worst case scenarios. Of course, when you're looking at the time complexity of algorithms and space complexity, there's often a best case scenario, worst case. Sometimes there's a separate average case. Take, for example, quicksort. In the best case and usually the average case, it has O n log n time complexity. But there are scenarios where situations, depending on how the input data is comprised, where it will perform much worse, O n squared. So that's pretty extreme example. That's pretty big difference in performance. Now there's ways to mitigate that. I talked about this in my first project, where you can randomize the pivot, or if you know your data is going to be kind of in a certain format, like it's going to be sequential, you can always pick the midpoint, and that will optimize quicksort. Why are you sorting if it's already sequential? Well, it might be mostly sequential, but not exactly. So, but if it's mostly sequential and the midpoint, it's going to be roughly the middle value, then you can use that as your pivot. And the way you do that, you can still use the first element or the 0th item in an array, but you just swap it out. You swap it with the other one and then go from there. So you can still treat it the same way. But anyways, that's one example. Then you have some that merge sort. Merge sort, the complexity on that's pretty consistent. It doesn't matter if the data is already sorted or if it's complete random. It doesn't matter. It's going to take the same amount of time to complete that entire operation. Now, on space complexity, kind of similar situation. Different algorithms use more memory. But today, I kind of want to talk about the two algorithms I chose for each problem, sorting and searching. And for sorting, I chose to go ahead and use quicksort, and I didn't have to change much. I pretty much used what I had from the beginning. And interestingly enough, the way I did my divide and conquer project, I actually included a sequential set of numbers just out of curiosity. And I saw then that without using a random pivot, it caused a lot of performance problems, and it would quickly have Stack Overflow exceptions. But anyways, so I'm kind of using the same quicksort algorithm, just changed a little bit so I can choose between if I want to use a random pivot or just use that first element. That way I can show the worst case very clearly. Now, I didn't want to use merge sort again. I wanted to do something different. So I went ahead and made a heap sort. And I did two different variations of it. I did one that's iterative and one that's recursive, just to kind of compare them a little bit. Recursive will probably use more memory because it has to store everything on the call stack. You call the method over and over. Every time you call a method, it pushes that on the call stack, and then once that method finishes, it pops it off the call stack, and kind of works its way back down. But anyways, nice thing about heap sort is that it's an in-place operation. So is quicksort, but quicksort actually executes. It has two recursive calls every time, so it really starts building up on the stack. And the thing is, if you want to implement it iteratively, you can, but you will still have to implement your own manual stack. So it's still going to take up the same amount of space. Whereas you can do an iterative version of heap sort, and there's no need to store anything in a stack. There's no external data storage required. You're just swapping variables around. So anyways, I'm gonna go ahead and look at my code real quick. Nothing too exciting here. I'll just share my desktop, make it easier so I don't forget to switch applications. But anyways, as you can see, here's my quicksort. just has the kind of an entry point, I guess you could say, just to make it nice and friendly. And that actually calls the recursive quick sort down here, just to kind of recap. As you can see, like I said, it's calling itself twice per recursive call. So it's doing a lot of recursion. This right here, I did not need to make an entirely separate method just to pass in a true or false for my random pivot. And all it does is determines if on the partitioning side, if it's going to swap with a random index or not. But there's no reason really to create a separate method. But the way I handle my tests to make it easier, so I'm not rewriting a bunch of code over and over, it makes it easier just to make it a separate method. So I have quick sort and quick sort 2. And then we'll jump on down. I'm not going to talk about how it works. It's the same thing as what I used before. I did not change anything. Go on down here to here's heap sort. This one here is a recursive heap sort. So you can see that it's calling make heap, and make heap calls that, and then inside of make heap it's also calling make heap. So that's recursive. But it's also, of course, doing the swapping as you'll see in heap sort. A lot of swapping, and it swaps from all over the place. That's kind of interesting to note, because the complexity of heap sort is O n log n. It's constant. It doesn't matter, it's like merge sort. It doesn't matter what your input looks like, how it's arranged. It's always going to be O n log n. So it should perform similarly to quick sort and merge sort, but in practice, as we know, things don't always work out perfect. Hardware architecture, it affects how things are processed. Not every operation costs the same computationally. Looking up things in memory, when you're doing a lot of swapping over a wide range of memory locations, it's slower than when you're accessing memory that's closer together. There's a term for that. I forget the term. But anyways, let's see here. But yeah, so that's one of the problems. So heap sort actually performs slightly slower than quick sort and merge sort. I mean, it can actually be significantly slower, really, not a huge amount. I mean, it's not like it's no longer n log n, but it's going to perform worse. The advantage is, like I said, it's in place. There's no extra memory required. Of course, when it's using recursion, it is pushing things onto the stack. So that is going to incur some memory. But now we move on down to heap sort 2. And this is iterative. It calls build max heap, and this actually builds the heap. It does that one time, and that's it. Once it does that, it's done with that. And then everything else gets performed with a for loop and a do while loop. So yeah. So anyways, quick look at those. Let me look at my search algorithms. These are so simple. Sequential search, we're literally just doing a loop, iterating over the entire list, and we're checking if the item, what we're searching for, is on the first item, it's on the second item, it's on the third item. You keep doing that until you reach the item you found or the end of the list. I'm just going to read my particular method. I just returned the index of where the found item is, or -1 if it was not found, because you can't have a negative index in an array or a collection. And technically you could, I guess, in C# have a negative, but normally you would not, unless it was a custom collection. But anyways, binary search, it's divide and conquer. You start a midpoint, you break it in half, and you look, hey, is this bigger than or smaller than that midpoint that you found? If it's bigger than, then you divide the right side in half, and you'll do the same thing there. Is it in that midpoint? No. Is it bigger or smaller? If it's bigger, you take the right side, you split that in half. You keep doing that over and over. And so you can see it right here, where this is if it's actually equal to that midpoint you pick. Then great, we return that. That's our answer. If it's not, if it's less than, then we basically set our max to the middle, -1. So that gives us and their minimum stays the same because it's still all the way to the left. We're going to now look at the left half of this collection or this list, this array. Same thing as if it's not if it's greater than the midpoint, we make the minimum equal to the middle plus 1. The max stays the same. It's already to the far right. So now we're going to start splitting that side and doing the same thing over and over. It's iterative. There's no reason to have to do this recursively. You could do it recursively, I suppose, but it's just as easy to put it in a while loop. And anyways, keep doing that. Same process. Once we find it, we return it. If we don't find it at all, we return -1. Interesting thing is sequential search. Best case scenario, 01. If the item you're looking for is the first item, bam, you found it. It's that quick. It's actually the same thing with binary search. If it is the middle item at the midpoint, if it happens to be there, bam, you're done. That's it, 01. Worst case scenario, sequential search. The item you're looking for is at the end of the list, or technically, if it's not in the list, it's the absolute worst case. We'll just say that the last item is the worst case. It's close enough. But anyways, if it's the last item where it's not in the list, you've searched through the entire list, and so it's ON. Takes the entire list. Binary search, it's quite a bit better than that. It's what, O log n, I believe. It's that's the absolute worst case scenario. So it's not bad. It's pretty doggone fast. Now, one important thing to note is that binary search does require that the list of items already be sorted, but a lot of search algorithms require that. If you're using a binary search tree, if you're doing red black tree, all these good things, those tree structures, you're already having to process your data and put it in some kind of a certain form. So we're just going to assume that anything we use in here is already sorted. Now, the .NET framework for collections already has like a binary search and a sequential search built in. The binary search will not give you correct answers if you don't, or will not give you the right results if your list is not sorted, but they provide it built in, so it's there if you need it. And a lot of times, if you're going to be using it, you will know ahead of time that you need to have your collection pre-sorted, because usually you're not just going to sort it and then search for one thing. Usually, if you're going to be doing binary searches on things, you're going to want it sorted. It's because you're going to be doing a lot of searches for things over and over. So the overhead of sorting at one time is not that big of a deal when you're doing multiple searches through that collection later on, or if you're sorting the list as you insert items into it, or something like a dictionary or I don't know, hash table, that kind of thing. It's already sorted. But anyways, let's look at our sort test. This is the same test I used before. I have cleaned up the code a little bit, made things a little bit prettier here and there. One thing I did do, I moved out my methods for generating things like random lists, sequential lists, because I could potentially use those other places. So I just broke those out in a little helper function here. One thing I also did, I'm no longer using, I'm no longer using a static stopwatch for the entire algorithm test helper. Instead, I'm creating the stopwatch every time I run my time algorithm method. And there's a reason for that. I wanted to play around with parallel programming, and you'll run into concurrency issues when you're trying to access the same stopwatch from multiple threads. You just can't do it. You're gonna have race conditions, and it's gonna cause all kinds of problems. So I went ahead and made that an instance or a local variable, and I'll show you why I'm doing the parallelism, why I'm using that. It's kind of neat here though, because I can just add in all my methods, all my different sort methods. I can add them to a collection, to a list that just contains these actions, which is a delegate. So it's basically passing in methods as a parameter. I'm just passing them all into a collection. That way I can just loop through it. Man, I just choose which ones I want in it, and I can go down here and right here. I'm just doing a for each, and it goes through every single sort method. So I'm actually running all of them on this and testing them all. Everything but bubble sort. It's so slow. It's terrible. But as you can see, I I'm actually going to test each algorithm for every data set 1,000 times. Why? Why not? I wanted to get really good data, and I wanted to kind of hammer my CPU a little bit. So I added in this nifty little parallel.for. It looks like a for loop. It's a regular method. It's not actually a for loop, but it functions like a for loop. Parallel.for, you give it the minimum, you give it the maximum non-inclusive, or yeah, exclusive, I guess you would say, non-inclusive max, and then you give it a variable name, and this is a lambda expression, so we have a anonymous method here. You could also pass in an actual method name if you wanted to, so we could call a method you choose, or you can just do an anonymous method right here. So it's basically an inline method. And then inside of this is it's actually making a copy of the list just for this thread, and actually timing it and storing it. Now, here's the important thing. You can't access the same memory from multiple threads at the same time, the same variable from multiple. You can, and there are certain tricks around that. You have to lock things, but you run into race conditions and concurrency problems. So, but you can access individual indexes of an array from separate threads. As long as they're not accessing the same index, you won't have a problem. So I just created a array with the same size as the number of iterations I plan to execute. And that's going to store each elapsed time for each run. So it's doing 1,000 of these. It's storing 1,000 elapsed times in milliseconds. And then once it gets done with that, and what Parallel.for does, it looks at your hardware. It knows how many cores your CPU has, and by default, it will use whatever's appropriate for your hardware, and it will automatically, every iteration, it will hand off to a separate thread. So it might do, there's no guarantee on the order. It might do 1, 5, 4. They complete at different times, but they all execute in parallel. When one finishes, it just holds off on that one, and then it goes to the next iteration that's available. And eventually it will complete all 1,000 of them, basically doing 8 at a time. And once it's all done, then it exits that method, and then control gets passed on. Now, then I'm just displaying the elapsed.min. That's a lenq method to just automatically get the minimum of a collection. So kind of a shortcut to finding the smallest value. Yeah, I'm cheating here, whatever. But who cares? It's just a display, just to make it pretty. And it's just kind of neat to see kind of finding the lowest execution time out of 1,000 runs for each data set. But we're doing, let's focus on what we're doing here. We're looking at everything from 100 to 10,000 with an increment of 100. And that's just the size of the data we're looking at. And we're just putting in a bunch of random gibberish, basically random numbers to test that. We do it one time with random. It runs this method with random list. And I showed you that just a moment ago in my helper method. We're doing it once with random, one with sequential, and then reverse. Reverse is just basically decreasing, one's increasing. To test the worst case scenario for quicksort, it doesn't matter if you do increasing or decreasing, it's going to give you the same problem. If you're only selecting the first element, your pivot is on a value that's going to have everything to one side of that value. It's either going to be all to the right or it's all to the left. So when you make your partitions, you're going to have a partition with everything and a partition with nothing, basically. And it's going to keep doing this. Every time it partitions, it's going to have this problem. And it's going to keep, it's confounding problems. It's horrible. When you do a randomized partition, it's great when you don't know for sure what your data is going to be structured. It might be semi-sequential or whatever, but randomized kind of works pretty good. Generally gives you the best performance. Not always. If you know it's going to be sequential, you can always pick the midpoint, and that would give you the best. But anyways, so you can kind of see how my test works there. My search test, it's not too complicated. I did find out though, I could not do my parallel execution. I ran into issues where I don't know if it's doing some kind of a compiler trick in the background, or if it's doing some kind of a caching, or just some, I don't know, some kind of magic is going on. That when I was doing it in parallel, it only happened with the binary search, but maybe it's because it was so quick anyways. If I did one iteration of my parallel for, which means it essentially does it on the current thread, it doesn't even have to spin up any other threads, it would give me good values for how long it took to execute, 0.0012 milliseconds or something like that, but once I added in a whole bunch of iterations, 1,000, it would start executing it would execute one of them at the, what you'd think would be the normal speed. The rest of them would complete almost instantly. It'd be like 0.0001 millisecond or something. It was crazy. It threw off everything. So it didn't really give me good data to go by. So I quit using that. It didn't really affect the linear search for whatever reason, but it sure did affect the binary search. So I finally just got rid of that. We're just doing one iteration of each test case or test point. So all we're doing is looking at, first, we're looking at 100 to 1,000 items incremented by 100. So you're gonna have 10 different data points. And each time, for each data point, we're actually gonna test 100 things. And we're gonna do a search for 100 items within that data. So if there's 100, it's going to basically be searching for every single item in that array or that list. But once you get to 1,000, it's dividing up that 100, distributed evenly across it. I just kind of wanted to see, I don't know, I want to get a good way to really look at the performance over a larger computational, larger execution time. It gives me a little more data to work with, especially since binary search happens so fast that you have to start getting extremely large element size of collections for it to actually give me some decent data to look at. And this is like one of the few ways I could actually come up with that without having to have crazy large collection sizes. So like I said, so it's doing 10 things, 10 different data points, but each one is actually timing it while it's, and the timing happens over the course of searching for those 100 items. So searching for 100 items is all timed together. It's not timing each one separate. I just consider that all one big operation. Just this is just out of curiosity. This isn't really the main point of looking at worst case. This is just kind of giving me an idea, but it does kind of show that sequential or linear search is way slower than binary search. Test 2, this is where I'm really looking at the worst case scenario. And I'm looking at from 1,000 to 10,000 elements incremented by 1,000. So it'll be 10 data points. And we're only going to be searching for the last item. It's a sequential list. We just look for the highest value, which is however many items we have. Makes it pretty simple. We're just searching, actually, now that I think about it, we're searching for the item just outside of the list. So we're searching for an item that's not in there, but it's still the worst case. Searching for an item that's not actually in the sequence. But anyways, we do a search for that, and it should tell us the worst case performance for both of them. And a sequential or linear search should be the worst. So let's go ahead and let me test this. I'm going to set up right now to run the test for, yeah, it runs super fast. It's crazy. Even this, you don't really see good values. See, it's so fast. Those values here for binary search, there's almost nothing to look at. It's very little data. So you can see a little bit more on the first test where it kind of combines them all together. I did my usual validation. I like to make sure my methods or my algorithms are working. But yeah, so that's that. There's multiple ways I could do this. I'm just going to change my, I do this for testing so I can quickly debug and look at because this program is set up where you put it out, if you were typing this in the command line, you're typing the program name, you would pass it an argument for what you want to do. And like search would give me the search test. If I do sort, it will give me the sort test. So now if I run this, it's going to actually do, and you'll see this over here in program. It's just, I'm just using a switch statement. So if we want to do the sort test, I just switched to sort. So now it's doing all the sorting. And as you can see, you probably can't hear it, but my fan's just kicked up on my computer because it is hammering the CPU. You can see there that it's definitely hammering the CPU. It might actually affect the recording while I'm running this. It's maxing out all the cores. So I'm gonna go ahead and stop this. I don't want it to interfere with my video too much. I don't know if it interfered with it or not, but it might. But yeah, so it's doing a lot of processing. Every single one of these is doing it. There's 1,000 gets done there, 1,000 there, 1,000 there. So it's doing that a lot of times. I just kind of wanted to speed the process up and test more than just 100 per. I'm just gonna get some good data. So I know my thoughts. I kind of jump around on my thoughts. I'm trying to be clear, but I kind of jump around a lot. It's just kind of the way I am. Anyways, so that pretty much shows all the code and everything. Let's look at my results. Oh, pretty graphs, pretty charts. But anyways, here you can see how quicksort definitely performs better than heap sort. And this is with random data. We're looking at random data here. So, and this is an interesting thing to note, that quicksort with a random pivot actually performs worse than quicksort with a fixed pivot. And that there's a good reason for that, really, when you think about it. The data is already randomized. Doing the random pivot, it's just adding an extra step to every single time it calls partition. It's swapping, it's doing an extra swap. So it's not gaining anything. The data is already random. It doesn't matter where you pick your pivot from. Heap sort, iterative is slightly faster than the recursive. I kind of figured it would be, and that's what I got. Any little spike you see, it's not important. It's just for whatever reason, it slowed down during that. It could have been some background process that took over, or something Windows needed to do that was important, or it thought was important. But anyways, yeah, so that's what we expected. But now let's look at worst case. And this is what we're really testing here. It's what we're really looking at for this exercise. As you can see, quicksort fixed has horrible, oh, Amber Alert. Yeah, not around here. Quicksort has, with a fixed pivot, has horrible worst case performance. And it's, like I said, it's O(n) squared, and you can definitely see it. Everything else, I mean, it's off the charts compared to everything else. You can't really see where the other ones fall. And if we go down here to decreasing values, identical. There's not really any difference at all between them. It doesn't make any difference. It's still having the same problem. But as you can see, you can't see the values because they're so out of whack in comparison. But there's no real, I can actually do this. We can get rid of quicksort fixed, and then we could rescale this. I'm just going to do this one. It doesn't matter which one I pick. And we're going to rescale this to, yeah. So there you can see the performance. Look at there. There's 0.5 milliseconds. And where does quicksort random end up? It's actually slightly faster when the values are already slightly sorted. So it's doing less work, believe it or not. And if you look at the time for merge, or for heap sort, It's pretty close. It's similar. It's there's 2 milliseconds. So, between 2 and 2.5, so like maybe 2.25. And then down here, we're like right at 2, maybe a little bit. So it might be a little bit faster for whatever reason when we had decreasing values. I'm not sure why that is. It really shouldn't perform that much faster, but for whatever reason, it does a little bit. I'm gonna do that again on here, just out of curiosity. Now I'm curious. Yeah, so yeah, same kind of the same situation. Although heap sort iterative really performed worse. Wow, that's interesting on the increasing values. It's kind of hard to compare them perfectly because there's so many optimizations and things that take place, compiler stuff and memory, how it's, maybe the way it's the data is, swapping memory in and out. Heap sort does a lot of swapping from all over the place. It maybe when it's sequential, it has an impact on that. I don't really know for sure. A lot of that gets down into how the hardware is accessed, how it performs. But excuse me. Anyways, regardless, it shows very well, I think, how drastic the performance drops off on worst case scenario. So moving right along. I know I get long-winded. I'm sorry. I just talk and talk. Looking at these, comparing these, it's really hard to generate a good-looking chart that's not logarithmic. I could make it logarithmic. It's gonna mess everything up. I can make this logarithmic, and let me just reset these. There we go. There's logarithmic, so you can kind of see a little bit what's going on, but it's logarithmic scale is very hard to understand visually. On this one, I don't think it would really help much on this because the data points for binary on the worst case was so flat, it just didn't seem to matter. I mean, it actually like gets faster and slower, faster and slower. It hardly ever got slower. But yeah, there's logarithmic scale, just if you're curious. But anyways, the point is, worst case scenario on sequential search is way worse than best case scenario on binary. And there's no real reason to even show the best case scenario because they both have the best case. And it's going to, however long it takes how many CPU cycles it takes to call the method and then figure out it's the first item and return back. It's going to be so fast. It's not going to be worth measuring. So no sense looking at it. But the worst case scenario of sequential or linear search is very poor. It's O2 squared. And yeah, you can definitely tell that. So anyways, that's my findings for this particular project. I hope somebody got something out of this. I certainly have a lot of fun doing this. If anybody has any questions over my code, one of the drawbacks to the way I'm doing my projects is that sometimes I need to go back and change code that I used in a previous project. So if somebody's looking at one of my previous projects and comparing code, some things might not match up the same because I might have changed things. What I could do is go through and tag. This is what I should have done from the start. Put a tag in Git on each, basically when it was ready for that particular assignment, tag it, and then it'd be easier to find that version in the history basically of Git. And you can see the exact, basically a snapshot of what the project looked like at that point in time. And something I should have done, but it's not a huge deal. I kind of like having it fluid where I can just kind of work and build on everything as I go. And I like having it be pretty modular as there's a lot of things I want to do, but I just don't have the time right now that would make this more elegant. There's some places that have some pretty sloppy code. It looks horrendous. My my knapsack test stuff, some of that stuff is so incredible. Not it wasn't not on the knapsack. What was the backtracking? I think I was working on some things and it was so incredibly ugly. But anyways, hope you all got something out of that. So my conclusion is that everything held true what I thought. Yay! That heap sort will be better in worst case scenario than quick sort, unless you take care of the issue with the pivot. That's a big issue. That's a big thing of quicksort. Quicksort is great. It's used in a lot of different sorting algorithms. The built-in sorting algorithm for .NET uses quicksort normally, but if the but it figures out it's a hybrid. It does some trickery to figure out if quicksort's the best. If it's going to be a situation where quicksort's going to be slow, it will switch over to heap sort. It never uses merge sort. Merge sort does use a lot of memory, so heap sort tends to be a lot better for that. But and then on the search, of course, linear search was way slower than binary search in the worst case. Best case, they're the same. So I had a lot of fun working on this one, and I hope everybody else did. And I hope you all have a great day. Thank you for watching.